So 11.5. So we've spent a little time talking about vectors. We're developing, working on our tools, the tools that we're going to use in for the rest of the semester and the rest of the year, really. And we have over all the math that you've studied, you've developed a pretty good understanding of geometry in the plane. You have a pretty good language for, pretty good tools for describing geometry in the plane. Well, now we want to take some of these tools that we've been working with vectors and start developing some knowledge of geometry in space. And vectors are going to be a key way that we're going to do it. So in the plane, we use slope to describe a line. That was kind of one of the most important characteristics of a line, is its slope. Well, in space, we need a little more robust, a bigger way of describing lines. So let me draw a picture here, and we will come up with a definition of a line in space. So here's our coordinate system, our nice right-handed coordinate system. So this is z, y, and x. And I'll draw my line in red. So here's a line in space. And we're going to say that point P, which is located at x1, y1, z1, and point Q are both on this line. And we'll call point Q x, y, and z. Those are our coordinates, some arbitrary point. This is our line L. Now in blue down here, starting at the origin, I'm going to draw a vector V that is parallel to this line. And V is our vector, just some vector A, B, C. So the line is through points P and Q, and L and V are parallel. We call V the direction vector for this line, because it's in the same direction. And we call A, B, and C, the components, are the direction numbers. And we are going to define a line in space as the set of all points Q and Q are just some arbitrary point x, y, z. We're going to define our line. This is the definition we're going to use. All points Q for which the vector PQ, where P is some point on our line, is parallel to V. That's how we're going to define a line in space. A line is the set of all points Q such that the vector from P to Q is parallel to this direction vector. That's going to give us a definition, a way to work with lines in space. So if our direction vector is pointing in a different direction, a line that's parallel to that vector is the set of all points such that for some arbitrary point on the line, the vector drawn from that point to another point is parallel to our direction vector. That makes sure we have a line in space. Yes.
So the direction vector could point in two ways, right?
Yeah, yeah. So it could point in either direction. They're as long as they're parallel. So the fact that these are parallel means that PQ is a scalar multiple of V. That's how we tell that vectors are parallel. So we can write a vector equation for our line. PQ equals some scalar multiple t times v, where t is a scalar. This is the vector equation for a line in space. This PQ equals TV. That's our vector equation for a line in space. So that's kind of like our y equals mx plus b in space. But we want a little more convenient way to work with lines in space, just so we have some more tools to work with our line. So what we're going to do is write out an expression for PQ and an expression for TV and equate our components, and that's going to give us a couple of different ways to work with a vector in space, or a line in space. So this is our vector equation. We're going to come up with a couple of different kinds of equations for a line in space, just like we did in the plane, where we have point slope, slope intercept, general form, etc., for working with lines in space in the plane. So this is our vector equation. We're going to write an expression for PQ. So from our drawing, the vector PQ is the vector x minus x1, these are our components, y minus y1, and z minus z1. So x1, y1, z1, the point P is some given point that's on the line. And we're going to say that equals the scalar multiple t times our vector v, a, b, c. And a, b, and c are our direction numbers. So we equate components. And we get x minus x1 equals at, y minus y1 equals bt, and z minus z1 equals ct. And I rearrange these because x1, y1, and z1 are given points on the line. So we're going to write in terms of our variable point that x equals x1 plus at, y equals y1 plus bt, and z equals z1 plus ct. We call this the standard or the parametric form of a line in space. So this is the standard or the parametric form of the equation of a line in space. This is the form that we will use most of the time, this parametric form. So we'll talk about finding a set of parametric equations for a line in space. So important things to remember here about our parametric equations. L passes through, the line passes through. So the line contains the point x1, y1, z1. So that's a given point on our line, and is parallel to the vector given by our direction numbers, a, b, and c. So when our equation of our line is written out in this form, in parametric form, we can pick out a point on the line, and we can pick out the direction vector. And t is just our parameter. So we're back to talking about parametric equations a little bit. But we can also, just like we did when we worked with parametric equations, we can eliminate the parameter. So we solve each of these equations for t. So we can eliminate the parameter. And to eliminate the parameter, all we're doing is solving each equation for t. And we can write the symmetric equations for a line in space. So when we eliminate our parameter, we get x minus x1 over a equals y minus y1 over b, and that equals z minus z1 over c. And that comes from solving each of these equations for t. And these are our symmetric equations. And from our symmetric equations, we get our point on our line, x1, y1, z1, and our direction numbers are the denominators of these fractions. So lines in space, a little more complicated than lines in the plane. We either have to deal with parametric equations or these symmetric equations. We deal with a set of equations for a line in space. So questions on our development. And I think this is kind of nice because it's really the first time that where we start to do a systematic description of talking about geometry in 3 dimensions. And that's part of what we do for the rest of the year, really, is use tools to start talking about geometry in 3 dimensions. Talk about surfaces, talk about planes, talk about lines, but we're not on a flat surface anymore. So like it opens up kind of the entire universe to us. It's kind of a nice thing. All right, so let's look at a couple of examples of the types of problems that you might see dealing with lines in space, and we will do a lot more with lines in space than come up with their equations. We're in plane geometry in Calc 1, we talked about tangents, our tangent line. In 3 dimensions, we'll talk about tangent planes, and we'll talk about normal lines that are normal to a plane or a normal line to a surface. We'll talk about tangent planes, normal lines. So there's a lot of things that we'll use lines for in 3 dimensions. Very similar to what we did in Calc 1 when we talked about maxima and minima and that kind of thing, but it's a lot bigger idea. All right. So let's say we want to find our parametric equations, and we'll do both sets, and symmetric. For our line through, we'll start with an easy one. Through -2, 0, 4, and parallel to this vector 2, 4, -2. So when we have our point to enter vector, that's pretty straightforward application, pretty easy application of what we just talked about. Our direction numbers are a equals 2, b equals 4, and c equals -2. And our point on our line, I'm just writing this all out. You don't necessarily have to write this all out to solve this problem. I'm just relating it back to what we talked about. And our point, x1 equals -2, y1 equals 0, and z1 equals 4. So we can say, so for our parametric equations, we write x equals -2 plus 2t. T is our parameter. Y equals 0 plus 4t. And z equals -2, sorry, got that backwards, 4 minus 2t. So there's our parametric equations. These numbers that aren't involved with the parameter are our point that we know is on the line, and we're multiplying the direction vector by our parameter. So there's our parametric equations. For our symmetric equations, we solve each equation for t. We get x plus 2 over 2 equals y over 4, and that equals z minus 4, and I'm going to put over 2, and we need a negative sign there. And those would be our symmetric equations. Direction numbers here, and our points are here. Questions there? And like Max pointed out at the very beginning, this line is also going to be parallel to a vector in the opposite direction. So we could have opposite signs on all of these, and we'd still have equations for the same line. It would just look slightly different. Our direction vector would be in the opposite direction. All right, questions there? Okay, let's look at another example. Just add a little twist here. We want to find our, we'll just do the parametric equations this time. For a line through 2 points. -3, 2, -3, and Q is 1, -1, 4. So we need two things to write our equation for our line. We need our direction vector, and we need 1 point on the line. So how do we find our direction vector? P minus Q. So the vector from P to Q is going to point in the direction of the line from P to Q, right? So we can just find the vector PQ. So I'm going to say PQ, the vector PQ is parallel to the line. So that can be our direction vector. So I'm going to write the vector PQ. I think I I did PQ, I think you talked about QP. Doesn't matter which one. So PQ is going to be the vector 4, negative 3, 7. So I'm just the vector from P to Q. 1 minus negative 3, negative 1 minus 2, 4 minus negative 3. So there's my direction vector. It could be go the opposite direction as well. Doesn't matter which direction, just as long as it's parallel. And so our direction numbers are 4, negative 3, 7. So A equals 4, B equals negative 3, C equals 7, our direction numbers. And doesn't matter which point on the line we pick for our x1, y1, z1. Doesn't matter, we can pick either one. And it's going to be fine. So I'm going to choose point P. I choose point P. So we'll say P is our point on the line. I could pick point Q also, doesn't matter. So I'm going to write x equals negative 3 plus 4t, y equals 2 minus 3t, and z equals negative 3 plus 7t. So that would be a set of parametric equations for the line through these 2 points. And when t equals 0, I get this point. Questions? All right. So the other thing we're going to talk about today having to do with lines is how to find the distance from a point in space to a line. Finding the distance between a point and a line is going to be a useful tool to have. So in the plane, how did we what tool did we use for distance? What was our main tool for distance? Distance formula, which comes from Pythagorean theorem. So in the plane, the Pythagorean theorem is a big tool for distance. In space, it becomes a little more to apply the Pythagorean theorem. It still applies in space, but you have to do a little more work to apply the Pythagorean theorem. So we're going to use a different tool. So let me draw a picture here. Here's our line. And here's our point P. Let me call this point Q. So there's our point. We want the distance from Q to the line. So what we're going to do is we're going to use vectors. So I'm going to pick some arbitrary point on the line P. So I'm going to call this point P. And I'm going to draw the vector PQ. We'll call this angle theta. And this distance is the distance that we're looking for. Well, there's some vector that we've talked. We know if we have the equation of this line, we know a vector that is in the direction of the line. I'm going to draw that down here in blue. And let me undo that. I want this to be centered at my point P also. And let's call that vector U. And U is a direction vector for the line. Well, looking at this diagram, what is the magnitude of this distance? Using, if this is vector PQ here. What would be the magnitude of that distance? PQ, the magnitude of PQ, times the sine of theta. So this is magnitude of PQ, sine theta. Well, is magnitude of PQ sine theta a quantity that we are somewhat familiar with at this point? E equals the magnitude of PQ times sine theta. What quantity have we been talking about that has to do with the sine of theta? A cross product. PQ sine theta, magnitude of PQ, times sine of theta is the magnitude of PQ cross U divided by the magnitude of U. PQ sine theta is the magnitude of PQ cross U divided by the magnitude of U. If I divided this cross product, PQ, magnitude of PQ, times the magnitude of U, times the sine of theta, that's the magnitude of the cross product, divide that by the magnitude of U, and I get PQ sine theta. So our distance, so the distance between a point and a line, is the magnitude of PQ cross U divided by the magnitude of U. Q is a point, the point that's not on the line that we're interested in. P is some arbitrary point on the line. We just form that vector PQ. We pick a point on the line and form that vector. And U is a direction vector for our line. So to find the distance between a point and a line, we use a cross product. Very nice, clean way that we can use the cross product. To me, that's a really cool thing. We don't even have to deal with the Pythagorean theorem and all those square roots and squares and all that kind of thing. Just cross product. And then when we talk about planes, we'll talk about the distance between a point and a plane. We end up using a dot product for that. So our dot product and cross product turn out to be very, very useful in geometry, not just for work and torque. All right, let's do an example of calculating a distance, and then we'll be done for the day. So we want the distance from the point Q is 115 to the line given by our parametric equations, x equals 1 plus t, y equals 3 minus t, and z equals 2t. So we need two things to find our distance. We need a point on the line. Any point. And we need our direction vector. How do we find a point on this line? We can use 1, 3, and 0. So basically what we're doing is substituting t equals 0 for a parameter and that gives us our point on our line from our parametric equations. So that's our points. Our parametric equations always give us a point on the line, the 1, the 3, and the 0. And that's equivalent to substituting t equals 0 for our parameter. So I'm going to write that down. I'm going to say at t equals 0, a point on the line is, we'll call it P, is 0.130. And our direction vector we get from these coefficients on our parameter. We'll say V equals the vector 1, negative 1, 2. So now we're set. We're going to form PQ, take the cross product with V, and find its magnitude. So the vector from our point on our line to our point not on the line, PQ, is going to be the vector 0, negative 2, 5. So I'm just finding the vector from P to Q. And then we're going to form our cross product with PQ and V. So PQ cross V. Write out my determinant here, IJK. 0, negative 2, 5. And 1, negative 1, 2. Form that cross product. I always do it all in steps. So I get I times negative 4 plus 5. Don't forget this minus sign here, minus j times 0 minus 5 plus k hat. This is the place where most people make mistakes when they're doing cross product, is some sign error here. K hat times 0 plus 2. So my cross product is I plus 5j plus 2k. And finally, our distance is the magnitude of this divided by the magnitude of our direction vector. So our distance is the square root of 1 plus 25 plus 4 divided by the magnitude of our direction vector, which is the square root. There's where our square roots come in, is these magnitudes of 1 plus 1 plus 4, and I get the square root of 30 divided by the square root of 6, or the square root of 5. So the distance between that point and that line is square root of 5 units. So we knew it. We talked about the Pythagorean theorem. Here's kind of where the Pythagorean theorem comes in, is in the magnitudes of those vectors. All right, questions there? So we just kind of came up with a whole new way of thinking about space. Guess I didn't really need to talk to you. Phone rings like once a year. Tomorrow, or on block day, for those of you that are going to be here, we'll talk about how we describe a plane in space. And that has to do with normal vectors. All right, so our homework.
No, I haven't yet.